Kia ora, Year 13, and welcome to a lesson on complex numbers. This is technically our first lesson on complex numbers, although I did go through some stuff when we did the health survey. So I'm going to kind of skip over exercise 11a. However, if you weren't there during that time, or you can't quite remember some of the stuff, maybe have a look at exercise 11a. Just as a bit of a recap, it should be relatively achievable from this quick summarization, but if you've got any further questions, please just ask. So we're going to quickly go through it, exercise 11a stuff, and then we're going to go on to exercise 11b. Again, that's going to be a relatively quick process. There's not much that I really want to cover on it, and I just want to get you guys working on some questions. So the first thing to know is that you can square root a negative. It's just that it's not a real value, it's what we call an imaginary value. And the square root of -1 is just I. If I was to do square root of another number that's negative, such as square root of -4, what you can say is it's the same as having the square root of 4 times the square root of -1, which square root of 4 is 2. Square root of -1 is just I. So square root of -4 is 2i. And you can always split up any rooted negative into a root of a positive times root of -1. And that's pretty much how you get any imaginary solution. Okay. Similarly, if you had a phrase now as x squared plus 1 equals 0, you can rearrange it to x squared equals -1, which is x is the positive negative root of -1, which is x is plus or minus I. So don't forget, plus or minus still exists when you're doing a square root. That's just for one little thing to do with that. And then I wrote out some statements here. Okay, so if I is root -1, then I squared would be root -1 times root -1, which just gets rid of the roots to give you -1. I cubed would be root -1 times root -1 times root -1, which is the same as what that becomes, which is -1, times root -1, and root -1 is I, so I cubed is -1 times I. Okay, I to the 4 would be root -1 times itself 4 times. Each one of these double pairings becomes -1, and -1 times -1 is just +1. So, based upon these four things, solution of root -1, -1, minus I, and 1, in reality I could rewrite this as just I again, I is just I, to make it a bit more symmetrical on the end values. I -1, minus I, +1. Basically, if you've got I to the 27, what you can consider is how many I to the 4s are in I to the 27, because I to the 4 is 1, and every fourth power I is 1, so I to the 8 is also 1, I to the 12 is 1, I to the 16 is 1, I to the 20 is 1, I to the 24 is 1, 6 lots of 4, and that would leave power 3 left over, which is just the same as saying that I to the 27 is the same as I cubed, and I cubed is just negative I. Okay, so that's one of the little things you can do with high powers of I. Divide by 4 and keep the remainder. Okay, so that's pretty much it from exercise 11a. We're now going to just quickly look at some stuff to do with complex numbers. Okay, so complex numbers and imaginary numbers are not the same thing. There's crossover, obviously. An imaginary number is specifically I, the root of a negative. Okay, but a complex number is written as most commonly as something like z equals x plus iy, where x and y are real numbers. Okay, And z equals x plus iy has a real and an imaginary part. Okay, the real part being the x part, and the iy being the imaginary part. Even though y is in itself a real value, it's a real value times a number of imaginary values, so it's considered an imaginary part. Okay. So yes, we can say the real number x is called the real part of z, which can be written as R E Z, RE meaning real value, Z being real part, the complex number, and the real number y is called the imaginary part of z, which is IMZ. Okay, the imaginary part of z. There's a couple of statements which I haven't included on here, so I'm just going to move this down and put them in here. Which is if x is 0, sorry, so when x equals 0, z would equal iy, which means z is completely imaginary. And when y equals 0, z would equal x, which would mean z is completely real. Yeah. So a complex number is written as z is equal to x plus iy. X and y are real numbers, I being the imaginary unit value. The real part of z equals x plus iy is called x, and the imaginary part of this is y. Y is the imaginary part, but it's a real number. Okay. If you have equal complex numbers, such as a complex number z1, which is x plus iy, and a complex number, a second different one, which is just a plus ib, so just same structure x, y, but with a, b instead. If you know that z1 is equal to z2, or you want it to be equal, then that must mean that the real parts are equal, so x is a, and the imaginary parts are equal, so y equals b. So if two complex numbers are equal, the real parts are equal, and the imaginary parts are equal. So that's useful for something that you can use later. Okay. The other thing to know is something called a complex conjugate. So if you've got z equals x plus iy, then the complex conjugate of z is written as z asterisk. Okay, and it's like a 6-pointed star, but it's an asterisk symbol. And z asterisk, the conjugate, would equal x minus iy. So the x values, the real part, are the same, but the imaginary part is the negative of each other, basically. So let's have a look at questions. I'm not going to go and do the questions because, well, the first one's just about using a quadratic formula, and the second one is a bit of a solving question, but I'll just talk through it. So if you had the quadratic 5z squared plus 14z plus 13 equals 0, and you want to solve it, then you can use the quadratic formula. You know, your minus b plus or minus square root b squared minus 4ac over 2a, where a would equal 5, b would equal 14, and c would equal 13. Okay, so straightforward, substitute it into the equation. Get to this point here where you'd normally, in previous years, go, oh, I can't go any further because that is not going to be real. However, at this point, we can now rewrite root minus 64 as root 64 times minus 1, which is the same as saying root 64 times root minus 1, which becomes 14 plus or minus 8i over 10, which can then be rewritten as its plus form and as its negative form in simplified versions, dividing through by 2 top and bottom. One of the things to note is that when you do the quadratic formula, solving a quadratic, when you get imaginary values, you always end up with complex conjugates. That's because this front part is going to be the same in both. So the real part is going to be the same in both, but the imaginary part, which comes from this root minus 64, is going to be the positive negative versions of each other. And as we just said a second ago, if the reals are the same and the imaginaries are positive and negatives of each other, then it's complex conjugates. And we can use complex conjugates for some other things. The second worked example from the book is if you have 2x plus y plus y minus 5 equals 0, find the values of x and the value of y. So this is using that second, or was it the first one? First one, the equals. You can consider this as two different equations. Sorry, two different complex numbers, a real complex oh, hang on, is that what we're doing here? No. Oh, okay. Oh, well, yes, actually, we can. Yeah. So we consider this as 2x plus y plus y minus 5. Instead of it just being equals 0, you can say is equal to 0 plus 0i. Okay, the imaginary part, sorry, the real part must be 0, and the imaginary part is also 0. Okay. So then you can say 2x plus y must equal 0, and y minus 5 must also equal 0, and because they are, well, you could make them equivalent to each other because they're both equal 0 and make a substitution that way, or the rearrangement of y minus 5 equals 0 is y equals 5, with a substitute back into here to find out what x equals. So, yes, the real trick here was writing it as 0 plus 0i, using that identity of equivalence. What did I call it? Equal complex numbers. Okay, if that complex number is 0, then it's 0 plus 0i. Okay, the last thing to look at are the 4 main operations to do with complex numbers. So what happens when you add, subtract, multiply, and divide? So if you have z1 and z2, defined by 2 plus 3i and 8 minus i respectively, if you were to add z1 and z2, it's just the same as adding the values together to get an overall value. So it's just collecting like terms, as you would with algebra. Same with subtraction, just collecting like terms. 2 minus 8, 3i minus i, or minus i in this case, to get you 4i. So standard expectations with addition and subtraction. With multiplication, if you were to multiply these two brackets by each other, or these two complex numbers by each other, when you expand out, you'll get your 2 times your 8, which is 16, 2 times minus I, which is minus 2i, 3i times 8, which is plus 4i, and then 3i times minus I would be minus 3i squared. And if you go back to what I said at the start, I squared is minus 1. So you can say if I squared is minus 1, then minus 3 times minus 1 is just positive 3, which leaves you with just 19 plus 22i. So when you multiply two complex numbers by each other, you still only ever you should, I think, only ever end up with a real part and an imaginary part, and no I squareds or I cubes, because you can deal with it based upon this set of instructions here. Okay. Another multiplication, which is quite common, is timesing by its complex conjugate. So if you were to do z1 times the complex conjugate of z1, which is 2 plus 3i times 2 minus 3i, what you end up with is just a real number. Okay, because the imaginary values will cancel each other out in the middle, and then the imaginary times the imaginary will generate a real value, because it'll be imaginary squared, which is a real number, minus 1. So that's kind of useful, especially when it comes to division. Okay, if you've got this question here, z2 divided by z1, 8 minus I over 2 plus 3i. The way to solve this, or simplify it in any way, is to use the complex conjugate of the denominator to turn the denominator into a real value. Okay, you want your denominator to be real, so when you multiply by the complex conjugate on the bottom, you have to multiply the top as well, and actually it becomes a combination of the two multiplication answers that we had a second ago, or at least similar to. Yeah, no, it was exactly that. Well, I don't know why the answers changed from there to there. Oh, because it's complex conjugate, sorry. It's not a combination of the previous two. So yeah, the bottom will be what we did with the complex conjugate. Here, it became 13. Okay, the top is the same style of expansion, but because it's a complex conjugate, not the original, then we're going to get a slightly different answer. So 2 times 8 is 16. 8 times minus 3, minus 24. Minus 1 times 2 is minus 2. And minus 1 times minus 3 is positive 3i squared. I squared being minus 1, meaning this positive 3i squared becomes negative 3. And then simplify it down to 13 minus 26i over 13, which both top and bottom share a common factor. So solution is just 1 minus 2i. And that's it. Okay, that is pretty much everything for today. It's just about, can you add, subtract, multiply, and divide? So adding and subtracting, collecting like terms, multiplying, expansion of double brackets, which you should be able to do, and using the identity from the start that was mentioned. And division is the only really big one, which is just complex conjugate of a denominator, multiply top and bottom by that to get it to be a real value. That's it. Okay. Good luck with all that. Have a go at exercise 11b. It's on page 272. If you've got any questions, please send them my way. And I'll speak to you again probably tomorrow, because I don't feel like this requires 2 lessons, although yeah, probably tomorrow. But if you need to not watch the video tomorrow and watch it at a later date, that's also fine. Okay, alright, I'll speak to you again soon. Bye.